I'd like to share a concept related to the interpretation of the uncertainty of the shear strength mole Coulomb parameters of soils. In the figures, we can see two sets of results. Let's call them scattered and robust. I do not want to discuss their quality right now. We can see that both groups of results give equal values of the effective internal friction angle and cohesion. One of the plots shows more scattered data. Thus, it seems to be less reliable. We are going to cover the following questions in this video. How can we compare these two plots in a quantitative and meaningful way? In other words, how can we measure the uncertainty of the obtained parameters? Secondly, how can we use this information for an assessment of characteristic values of the soil parameters? The concept presented briefly in this video is described in detail in the paper entitled On the Interpretation of Shear Parameters Uncertainty with a Linear Regression Approach. The paper is an open access article. Link is provided in the description of this video. Also, in the supplementary material, you can find a simple Excel implementation that allows for determining uncertainty of the soil parameters. Since you are still watching this video, it is likely that you know how to obtain cohesion and internal friction angle based on the laboratory results, so I'm not going to explain this in detail. However, I want to stress two things. Simple linear regression is used in the process. The variables used in the linear regression approach are different from those used in drawing more circles. From now on, I will focus on simple linear regression conducted on the S'(T) plane. S' stands for effective normal stress associated with the topmost point of a Mohr circle. The T' is the maximum shear stress. First, we need to find the parameters of the regression line, intercept T sub 0 and the slope angle theta. The obtained regression parameters are later transformed to the soil parameters that we are looking for. The previously mentioned paper covers the whole process. It is not the only possibility. In the provided Excel implementation, you will find an example with the regression on the plane of principal stresses, sigma sub 1, sigma sub 3. The first thing that comes to my mind when I am asked about assessing the simple linear regression results is the coefficient of determination, denoted as R². R² tells us how well one variable explains another one. In other words, how well the line can fit provided data. This is indeed a fair and straightforward measure, especially if we are looking for correlations. For the fixed slope of the line, the R² will be higher, which means better in more robust results. However, R² decreases also with the slope of the line. In an extreme case, if the regression line is horizontal, R² is equal to 0, even if the points fall very close to the line. That makes R² inappropriate for us because it depends not only on the robustness of the results, but also on the internal friction angle. Let's go back to the previous figures. How do we know which results are more reliable? Intuitively, we are more confident about the dataset in the right-hand side plot. This is because the points are closer to the regression line. The data in the left-hand side figure is more scattered. There is more randomness in it. Something might have gone wrong with one of the tests, and if the results of this test had been slightly different, the final parameters would be determined with better accuracy. Instead of repeating the test, we can remove one of the points from the dataset and see what happens. In the case of the more robust dataset, it seems to be okay to remove the point. The line doesn't change the position very much. The left line tilted much more. We can verify the change on actual numbers. Removing 1 point from the left-hand side figure changed the estimated internal friction angle significantly. In the case of the right-hand side figure, the difference is slight. We can imagine that regression line on the left wobbles as we conduct alternative tests on the same soil because of this randomness. The wobbling would result in a large spread of the regression line parameters, impacting the obtained soil parameters. The second dataset is more robust so that the range of possible values would be smaller. I am getting straight to the point. Well-established formulas allow us to estimate the probability that the regression parameter, slope or intercept, reaches a specific value. Let me visualize this in the form of the probability density function. The value obtained in the experiment, 18 degrees in case of the internal friction angle, is in the middle of the curve. The red line and the blue line corresponds to the scattered and robust results, respectively. The area under the curve is probability. If we cut out the middle part of the curve, such that the 90% of the total area remains on the plot, the field area, the edges will indicate the boundaries of the confidence interval. The confidence interval is what we are looking for. It is a range of the values of the parameter. We have a 90% probability that the actual value falls within this range. The 90% is just an example. We can choose to find 95%, 99%, or whatever we want. In the case of the blue line, we can see that the confidence interval is narrower. The narrower the confidence interval, the more confident we are about the results. Why is it good for us, and how can we use it to assess characteristic values of soil parameters? It is simple. Very often in geotechnics, we want to choose a characteristic value of the parameter with a significance level of 5%, 5% fractile. If our confidence interval covers the middle 90%, it lefts 5% below the lower boundary and 5% above the upper boundary of the interval. In such a case, we can assume that the lower boundary of the 90% confidence interval is the characteristic value of the soil parameter. This is why more robust results allow us to assume higher characteristic values of parameters than the scattered results. Of course, variability is an inherent feature of soils. One soil gives more scattered results than another. At the end of the day, it is not that important how robust the results are. We don't have much influence on it. It is crucial how confident we are about the results and whether we can justify our conclusions. The method presented in this video is not the only way to obtain confidence intervals. Other methods include taking into account local experience from databases or personal experience. You can find them described in other papers. For example, determination of characteristic soil values by statistical methods. However, this method allows you to conclude about confidence intervals solely on the basis of the result of one experiment. By one experiment, I mean 3 or more triaxial compression tests. A set of triaxial compression tests provides a lot of information. Why would you stick to the simplest approach and pick only 2 numbers when you can have a whole spectrum of values along with probability? You not only can have them, but you also need them. You can use this information for characteristic value estimation. Thank you for watching and consider learning this method.